The next thing I'd like to explain, it's going to take us a minute to get there, but the device is called transformers. Transformers are really cool. They explain why your phone charger and your Chromebook charger have that kind of block attached to them. Um, and if we push transformers, the logic of transformers also explains wireless charging. So to get to transformers, we need to backtrack a little bit. What we've done so far, especially that note with all the left-hand, right-hand rules, is we learned that whenever we have electricity moving through a wire, that creates a magnetic field around the wire. The flip-flop, the cool symmetry that they figured out way back when, and now we take advantage of all the time, is if we can use electricity to make a magnet, the flip-flop is we can use a magnet to make electricity. The key thing is, though, we have to have movement. You can't just hold a magnet near a wire and get electricity in that wire. But if you move a magnet so there's a changing magnetic field in the wires, then that changing magnetic field triggers electricity in the wires. And kind of like we saw before, we didn't do much with long straight wires practically. We don't build many things with long straight wires because the effect isn't very big. We use coils. So in all those earlier applications, the motor, the doorbell, the speaker, they all had coils in them because coils amplify the magnetic field. Similarly, when we're trying to make electricity, we'll use coils because coils would take advantage of that magnetic field and make more electricity. So basically, the bottom line is we can generate our own electricity. The fancy name for it is electromagnetic induction. Basically, this is what's going on at Niagara Falls. The earlier power plants were literally built around the corner from us in Niagara Falls. This is what's going on in a windmill. Basically, it is the exact reverse of an electric motor. So perhaps the electric motor, the explanation didn't stick very well. And unfortunately, that's going to have to be okay. But in a motor, current flowing through the coils made the coils spin a particular direction. If you took a motor, so maybe you take apart the hard drive in an old computer, your electric toothbrush, any electric motor, if you took it and used your arm muscles to physically spin the coils, that would create electricity in the coils. So if you're like in some sort of survival situation, if you needed to make electricity, all you need to do is get an electric motor, and instead of putting a battery in it, physically spin the coils, and that'll generate electricity. So you maybe have seen, they sort of joke over the years like you should attach an exercise bike to a TV and a kid has to ride the bike to make the electricity to power the TV. In that exercise bike is really just an electric motor being run backwards. Your leg muscles are spinning the coils, that's making electricity. Since we have so much falling water, we basically have a virtual, endless, clean supply of electricity. Same thing with wind. Okay, now a little bit of technical information. There's two forms of electricity, a form called AC and a form called DC. DC stands for direct current. That's what you learned in grade 9 electricity. That's what a battery does. A battery just pushes current or the electricity in the same direction around a circuit, just nonstop, always in the same direction. If we generated electricity at Niagara Falls that way, it would be very inefficient to send it over wires a long distance. So Tesla, Edison was all about DC. Tesla was all about AC. So thanks to Tesla kind of getting some support, these power plants were built with AC. AC stands for alternating current, and literally what it means is that the electricity alternates or sloshes back and forth. So for one split second, the electricity is maybe going forward in a wire, and then for the next split second, it's going backward in the wire. Then forward in the wire, then backward in the wire. Even though it's not always moving in the same direction, we can still harness that electricity and do everything with it. Why AC is better is it doesn't create as much heat. So think back to our conservation of energy kind of stuff. Friction creates heat, steals energy away. So AC doesn't create as much heat, so it's more efficient. So if you generate a whole bunch of electricity at Niagara Falls, more of that electricity will make it to your house if we send it as AC than if we had have tried to send it with DC. Also, so it's more efficient. Also, because of the way it alternates, there is a really simple way to change the voltage. So electricity can be generated at a very high voltage and then transformed to a lower voltage by the time it gets to your house. So power plant, I found this one. This is a terrible diagram. So look at that. Must be some sort of coal burning plant or something weird, belching out a bunch of pollution. Nowadays, let's say we get rid of that and replace it with Niagara Falls. They would have no pollution. Or maybe a nuclear power plant would have, wouldn't have any steam pollution like that. So old diagram, but it works anyway. They're spitting out some numbers. So this old diagram I found is suggesting that the power plant is outputting electricity at 12 kilovolts or 12,000 volts. It gets stepped up, so we're going to talk about transformers, all the way up to 400 kilovolts. So depending where you live in Waterloo, there's like those big metal hydro towers run through Beechwood. They kind of split Clare Hills and Columbia Forest, kind of. Depending where you live, you may be able to look out and see these big metal towers. These big metal towers have high voltage electricity running through them. Then these high voltage wires go into another transformer. This one's a step down. We'll talk about that in a bit. And you'll notice it lowers the voltage from 400 kilovolts. It drops down to 13 kilovolts. These substations, locally, if you're driving around, you can see there's a substation kind of on Fisher Hallman by the soccer fields. There is a substation across the road from the Sobeys. So Sobeys is kind of on a corner. Across the one way, there's like townhouses or some residential buildings. But across the other way, towards the University of Waterloo, set back from the road, there's a substation there. If you're into mountain biking, there's a big substation down by the one entrance to the hydro cut. So those substations are taking the high voltage and dropping it down to lower voltage. Then those wires run into our subdivisions, and in old days they used to have the transformers like on the top of a telephone pole, but we've gotten a little bit more clever. Now we've started burying the wires. They're more weather can't mess with them when they're underground. So for different reasons they've buried the wires, but then close to your house there has to be another step down transformer. So nowadays, in your subdivisions, you'll see like a green box on every few hundred meters on your street. The wires flow into the green box, and the green box does the last step down, so you have a lower voltage running into your house. In North America, we usually run 240 volts into your house, and then somewhere in your house there'll be, we used to call them a fuse box or a breaker box, and that sort of divvies up the electricity, sends some of it into your kitchen, some of it to your furnace, some of it to your dryer, your air conditioner. All your electrical circuits are powered off that 240 that runs into your breaker box. I'm going to talk you through what a transformer is, but this is already the key of why they're important. Because we're using alternating current, we can transform the electricity from the high voltage that gets sent down the wires to the low voltage that goes in your house. Inside your house, what we're going to talk about next is most of your outlets are only 120 volts, but you don't want to send 120 volts into your phone charger. 120 volts is a lot of volts, it would cook it. So you use another transformer so you send even less volts when you're charging your electronic devices. The key is, before I move on, is that we can transform because of this constant changing, forward and then backward and forward and then backward. So now we're going to talk you through the guts of a transformer and how they work. And there's one little equation you got to kind of be okay with. Skim through that. The principle of a transformer is that electricity makes a magnetic field, the stuff that we talked about in our note with all the left-hand, right-hand rows. And the stuff I'm talking about today is that a changing magnetic field can make electricity. That symmetry is what makes a transformer work. Electricity can make a magnetic field, and a changing magnetic field makes electricity. The reason why we need transformers, it's more efficient to get electricity from our power plants to your house, and practically we've designed these really cool electronic gadgets that are rather small with tiny wires in them. We couldn't take 120 volts from our household outlet and put all 120 volts into your phone. The wires in your phone are way too small. If you put them as voltage in them, they'd create a lot of heat and it would literally cook your phone. Don't try it at home. It would smell funky. It would literally burn the guts of your phone. So this little block that you all know and love, that we always lose, that we forget to take on vacations, or when we do take on vacations, we leave them there. Inside this little block is a transformer. Some of these little blocks also have a thing to convert from AC to DC. We're going to leave that out for now. Today we're just going to focus on the transformer part. Inside the block there's a transformer so that the 120 volts coming out of the wall plug is a lower number of volts by the time it goes into your phone. Alright, here's how a transformer works. Transformer basically has three parts. A metal core, which is this kind of, in our diagrams, are going to be rectangular. A primary coil. The primary coil is the side where electricity goes into. So it's the input side. It usually gets the subscripts of P. So we've got a primary current, IP, and a primary voltage, VP. And this coil has a bunch of turns on it. How many loops of wire there are is called the number of turns. It's going to be NP. So P for primary, a current, a voltage, and what we're going to come back to, it's important, is the number of loops in that coil. There's also a secondary side, a secondary coil. That's this coil over here. It's got a certain number of loops in it. It kicks out a particular voltage to the secondary side and a particular current. Okay, it's all typed out here. I'll talk you through it. Basically, alternating current goes into the primary side. So in this coil over here, so these loops of wire over here, the electricity is alternating or going back and forth. Maybe one split second it's going to the right when it's close to us, then the next split second it's going to the left when it's close to us. Let's say it's going to the right. When it's going to the right, it's basically going to be, it's going to turn that whole coil, that whole rectangular squared off O-shaped thing, it's going to use that, turn that whole coil into a magnetic field. There's going to be magnetic field lines, let's say pointing, this turns into a magnetic field, let's say the magnetic field at the split second is pointing up, that's going to wrap around and there'll be a magnetic field pointing down through that side. Then, because it's alternating current, a split second later, the electricity on this side, the primary side, goes the exact opposite direction. So I'm going to erase all this. A split second later, the electricity is going the exact opposite direction, which means a split second later, the magnetic field is going the exact opposite direction. So the magnetic field is going this way. So on this side, now the magnetic field is pointed upward. The bottom line is, as the primary circuit's current flip-flops from direction to direction, it creates a magnetic field that one split second is pointed down, the next split second it's pointing up. That creates a magnetic field over on the secondary side that's flipping. If one split second is pointing up, when the primary changes, the next split second it's pointing down. So basically what we get, the alternating current, since it's sloshing back and forth, it's creating a magnetic field that's also changing back and forth. That means that inside the secondary coil, there's a changing magnetic field that keeps flip-flopping over and over and over and over again. The whole point of today's topic, this induction thing, is the electricity makes a magnetic field and the changing magnetic field makes electricity. So in our secondary coil, this is exactly what we've got, a changing magnetic field. That changing magnetic field in the secondary coil is going to make electricity flow in the secondary coil. What's really cool about this is there's no direct electrical connection. These wires on the primary side aren't electrically connected to the wires on the secondary side, but by flip-flopping electricity on the primary side, we've induced or we've created electricity in the secondary side. All right, that's kind of what a transformer is. Now here's where, well, really, the one that's drawn there isn't really the best transformer. Here is a more realistic transformer. In a realistic transformer, there'll be different numbers of loops on the primary side compared to the secondary side. This kind of one that I'm showing here, this is exactly what would be in your phone charger. There'd be a lot of loops on the primary side and fewer loops on the secondary side. What that means is a large voltage goes in on the primary side and a smaller voltage comes out on the secondary side. We call that a step down transformer because it's decreased the number of volts. It's all about ratios. I'm going to show you the equation next, but if there are 10 times as many loops over here, let's say there's 100 loops over here and only 10 loops over here, so this would be like the number on the primary. If the number on the primary, it's got to be bigger. If it's like 100 and the number of loops on the secondary is only 10, since there's 10 times fewer loops, we're going to get 10 times less voltage. You don't have this kind in your house as often, but a step-up transformer is the exact opposite. There's fewer loops over here and more loops on the secondary side. So we can take a rather small primary voltage and it kicks out a larger secondary voltage. So maybe you've bought a funky appliance that's used to getting 240 volts, but you're putting it in a plug that only kicks out 120 volts. You would have to use a step-up transformer to increase the voltage. The math on transformers is it's all about ratios. If we know the ratio of the number of loops, it's the same ratio of the number of volts. So if the primary has 10 times more loops than the secondary, then the primary is going to have 10 times the voltage of the secondary. It's all it's all ratios on the loops to get the ratio of the voltage. I'm going to pause the video here. There's an example, a couple examples for you to try, a worksheet. And the last thing I want to show you then you can pause and look at those two examples, is the cool technology now is wireless chargers. So maybe you're an Apple person, you got some AirPod Pros, they charge wirelessly, or maybe your new phone charges wirelessly. Wireless chargers are the exact same principles as transformers. There's just an air gap between the primary and secondary coil. So in your charging dock, or whatever you call it, your charging pad, however you charge your wireless phone, the primary coil is in the one part of it, the thing that's plugged into the wall, and then the secondary coil is in your phone. And you just have to line them up properly so that the secondary coil in your phone is close to the primary coil in the charger, and the primary coil that's wobbling back and forth in the primary coil induces electricity in the secondary coil, and that induced electricity is what gets used to charge your battery. I've tried to find videos to explain this. This one that I found is pretty good. It gets complicated. Just watch the first 90 seconds. Well, watch as much as you want, but the first 90 seconds is kind of a nice summary. There's a check-in problem related to this, and of course, before you get too far, you're going to backtrack and try those two example questions. As always, email me if you have any questions.